All right, welcome to OneQuantum Nepal. So we are a group of quantum enthusiasts looking to basically sort of started like a nascent quantum ecosystem, right in Nepal. And we do this through weekly meetups, invited talks. We invite people, experts like you, right? We have mentoring sessions, right, where we match mentees with mentors. And we have like over 400 mentors registered, and we have like
That's impressive.
mentees, and we have 100 mentors, right, that are mentoring these mentees on a regular basis. And it's a community effort. We have chapters, Nepal chapter. We have chapters in South America, US, right? Nordic chapter, Europe, a lot of them in Africa, and you can see on the left, right? These are like things we do, and we help build community. And you see on number one, local content resources network for global quantum community, mentoring, like I said, career fairs. We have companies, come and basically have opportunities, right, to present what they do so that they can, basically attract new talents. And we also offer projects, real quantum projects. And in fact, in OneQuantum Nepal, we are working on a realistic quantum project called Grover's algorithm. And next week, Manish Singh, he's going to present, about that. It will be about simulations of Grover circuit on a real quantum device, right? And just as an advertisement, there is also this nice sort of event going on in July 19th and 20th, OneQuantum Women in Quantum. And I recommend, right, people to participate, because it's you will see talks or hear talks from experts in quantum, and there are career fairs from partners such as Google, IonQ, Honeywell, and it's sponsored by Keysight Technologies and IonQ. And this is led by Dennis Rufner from IonQ, who is the VP of business development. And I think it'll be pretty exciting, right? So I recommend a lot of you here to partake. It'll be pretty interesting, I'm sure. And finally, right, just a little announcement for our next meetup next week. We will have a demo, right, from Manish Singh. We'll sort of close the first quantum computing project, of Nepal, and we will basically run this simple quantum algorithm on real quantum device, and next week, July 22.
Yeah. Can you go to the first slide once more?
Yes,
please?
Exactly. Absolutely.
Awesome. So I see that this has 4 people only. Has there been changes?
No, there are 4 people to start with. 4 people to start with, and we are going to do more of such events. And you are as a second speaker, right? And I mean, I cannot forget to tell you that there will be 2 more from UCLA.
Thank you so
professor.
much for considering me. Very
No
glad
worries.
to be here. It's a great
Yeah, I
opportunity.
mean, your expertise is quite valuable for us, to understand. And I want to introduce, right, the speaker today. He's Rishabh Karna. We actually studied together back in Bremen in 2011, right? And he is a computer scientist and computer science educator, right? And he has diverse interests. He's interested in new technologies, right? And I mean, especially quantum technologies, right? And he will give us sort of an outsider's, or sort of like a bigger perspective, of what computing really is, at the fundamental level, and also at an abstract level. And for us, I thought it would be pretty interesting to hear from somebody like Rishabh, who has interest in quantum, but at the same time he possesses massive experience and knowledge, in basic computer science, classical computing, as well as abstract, theoretical computing. And Rishabh, thank you for doing this. We are very glad to have you at OneQuantum Nepal. And now the floor is yours.
Thank you so much, Manish, for such a wonderful presentation opportunity and this platform for exchange. I'd like to start my desktop sharing now. So I guess you can see me. And
Yes.
but at the same time, you also see my presentation. I'm logged in as two people, and in a sense, I am two people in this meeting because of two logins. So on one side, you might see my video, and on the other, you might see the slides. And I would like to focus on the slides now. So yeah, this is the title of the talk today. This title has been changed since Manish originally asked me. I was thinking of talking about some supersymmetries, some symmetries across time and space, and I was jokingly calling a supersymmetry. But we will still get there. We will think of what large scale projects have happened across history in the field of computer science, and because we will go through every different milestones in history of classical computers, as we would call it in a quantum conference. Uh, we might not be able to go through all the important moments. And I have to tell you that this is my biased reading of the history of computer science. And the bias here is I am filtering out the things that might be more interesting to a group of quantum computer scientists or quantum physicists who are now computer scientists. And the second part of the talk, it is a reference to a sci-fi novel. And maybe we'll have some fun towards the end when we come back to this idea of a timescape similar to a landscape. So let's get started fully. Let's get started with the the notion of what is grammar and why grammar when we talk of history of computing. Grammar is specifically because grammars are our rule books, our recipes for construction. In the constructivist dream, where we prove something using constructions, where we build up a structure by composing different constructions in a constructivist proof, where we build up things. So we build things up using a grammar. So any language, a formal language, which could contain maybe something like a programming language, or it could also represent some human languages or other abstract languages. We build them with grammars. And so this is a grammar talk in a sense. And I did not used to listen to a lot of grammar talks when I was learning, say, English language, and I still happen to learn it. Most computer scientists, we also do the same. We don't really delve so much into grammar, we internalize it. But that's why it's difficult for us computer scientists to talk to other people, because they don't know our grammar, the very constructs with which we make our language, and there is a communication issue. So we will go through different times in history of computers, of computer sciences, computational sciences. But first, we will also think of what computers originally meant. Computers used to be professionals who computed as a job. That was the whole idea behind it. Let's compute. Let's sit down in a room, calculate maybe fiduciary or other financial matters. We just do the calculations as a computer, and whoever would do this calculation, they were called computers. So computers initially were people. And then we thought, in the Alan Turing sense, when we were thinking of computers, we were thinking of, okay, this thing requires intelligence to do. What if the machine itself could do this? So the very first artificial intelligences we created were Turing machines. Computers, calculators back in the day were artificial intelligence. AI, essentially, in some sense, it's about whatever feels magical, too far away from the rest of the technologies. That is artificial intelligence. in a superficial reading of the term. And that was the AI back in the day. The very first computers were calculators. And that is exactly where we might be when we are repeating the same with quantum computers. So a Turing machine is very close to the notion of a computer because it is something equipped with, let's say, 7 kinds of mathematical objects in one interpretation. So it's a tuple, n tuple, or a 7 tuple, where you have 7 mathematical objects in this tuple. And there are some of these items in the tuple. They could have states, and there are certain symbols that are allowed and certain symbols that are not admissible to input or get as output from the system. That's essentially what a Turing machine does. You have some symbols which can be fed into it as an input, then it does some state changes, maybe it reads through a tape, and so there are different things going on, and at the end of the day, at the end of the calculation, you have what you are asking for. If the calculation stops, maybe the calculation goes on forever, there is no way to say that the particular calculation will actually stop. So it might go on forever. Regardless of that, what we can do is, whether or not our calculation goes on forever or has a finite amount of steps after which it finishes and yields a result, we can think of this whole operation of Turing machine itself as a set of strings. And now remember this, a set of infinite strings, it's very important for us. Almost everything we do within computer science is just a stream of ones and zeros, of strings, of symbols, of conceptual objects. So if you could encode the Turing machine itself as a set of strings, as a sequence of strings, and let's say we have a machine which runs these Turing machines, because now Turing machines are just symbolic. So if you have a machine that can run a Turing machine, then you have a universal Turing machine. So a universal Turing machine is capable of running any Turing machine inside it. It is a machine that simulates the running of other machines. And that is very close to the notion of a modern computer program, because computer programs are computers. And programming in computers for us is about being able to use the same machine for every different kind of use purpose. Otherwise, what you have is just a calculator and not a computer. So are you able to program it or not? You can program certain things in some graphing calculators, and now you can rightfully call that a computer. If you can only do an initial set of operations that has been hard coded into the system, then you are still using a machine which works like some automaton. And not all automatons can be called a computer, although they may be helping us compute. The essence of computing is in the generality of it. It's not in being able to run one particular kind of algorithm on one particular kind of device. Because as long as we are doing that, we are still doing electronics, not electronic computing. In the same sense, you might be doing quantum physics and not quantum computing. If we stick to just having a Turing machine instead of having a universal Turing machine. So this is the goal of the current quantum world in the theoretical sense. And one small note, this comes from a paper on computable numbers with an application to the Entscheidungs problem. This is, the problem is about decidability, whether a certain sentence belong in a certain language, whether a certain thing can be proven or not, can we actually calculate this or not. That is the computability aspect of decidability. So this, we were initially thinking of computable numbers, and that led us to having modern computers. So now we go back a bit again. Why is this so? That we are essentially saying, okay, here's the mathematical interpretation of what a computer should be. And what I have done is I have converted this into a set of symbols. And I have fed this set of symbols into the Turing machine itself, because this Turing machine happens to take other Turing machines as input. So in all this, you can see that what is happening is we are encoding a machine itself as a set of symbols. Information encoding has this general idea that you can take certain things which belong in a certain domain and use symbols from a completely other domain to represent them. And Gödel did this for a big crisis in the foundation of mathematics. He was not really thinking of becoming a functional programmer, and he ended up being the world's first and most famous functional programmer, pure functional programmer. And he did this programming before computers ever existed. So what he did in this Gödel encoding program of his was he created these functions which could convert sentences, mathematical propositions, into numbers. He had a nice encoding scheme is using prime numbers and prime factors. And so if a number can exist, if you can see that a particular number has some primality, it can actually exist, then the corresponding sentence representing that number also exists, which means your sentence is valid or admissible in this system. So this is a grammar checker that he's building. So remember that this is all about grammar, and he's building a grammar about representing computation in a computer, but before computers existed. So think about this. The quantum computer programs can also exist way before the actual quantum computers exist and are accessible to us. Another thing that was happening was we were also seeing the symmetry aspect. Sorry, I lost a bit of the track of time. Manish, can you tell me when we started, at which minute?
Yeah, we started, I think 15 past 15. Oh, sorry, I'm still in CST time. So you finished 15 minutes. I mean, don't worry, you have another half an hour, so no worries.
Awesome, thanks. So yeah, we will make one single pass through all of the presentations, and then we might go deeper into some of the topics because these points are very dense, and each of those points could warrant their own slides as well if we go depth first instead of breadth first. So we will jump across. On the other side, there was another mathematician. And all of these mathematicians are also just helping physicists like they always have done across history. So Kurt Gödel was there. He was actually solving Hilbert's problems. Hilbert had asked, are things decidable in mathematics? Do we have a foundation which is complete, which can explain almost all the mathematical objects? Can be built up from these primal, more foundational objects maybe? Is there such a foundation? If sets are those foundational objects, how do we do it? Because there are problems. We were seeing problems with sets all the time because infinite sets in naive set theory don't work well. So all these things were happening, but Hilbert at the same time also was asking Emily Noether to explain to them a bunch of mathematicians and maybe even Einstein himself why relativity works. And she also did something similar to what Gödel did, actually. I would argue that she did. She basically encoded the laws of nature into a more foundational law. The law that anywhere you are in the universe, whichever way you are facing, rotationally, angular, in an angular position sense, or wherever you are in, let's say, the Cartesian position sense in this universe, the laws of the universe remain the same. There is a symmetry in the laws of the universe. And whether you are hitting something else, or whether you are refracting off of something, or whether you are a photon at the speed of light, there are things that would work the same way. So she was the one who was not just doing information encoding, but she was also recoding certain information in terms of another more foundational law. And now with her, you could examine Euclidean spaces or Cartesian spaces with rows and columns, or X and Y axis or Z axis, or you could have Hilbert-esque spaces with infinite dimensions as well. And and there are certain things you can do using the same Noetherian laws and expect certain, what outcomes you can expect. Similarly, in Riemannian times, let's say after the advent of complex analysis, when we were friendly with the idea of complex numbers, this helped both quantum physics and relativity, because in both cases, we have the notion of imaginary time, or we often have the imaginary axis. And most of my quantum knowledge about quantum physics comes from being a roommate of uh, students doing maybe PhD or some research in quantum physics. I have secondhand knowledge of these things, but two of the things I think I should focus on would be whether or not you are allowed to observe a value within, let's say, this imaginary container. It has some quantum information, and I have been told that if I look inside it, it changes. Because the act of looking inside it is going there, hitting it, coming back. Okay, you disturb it even when by looking at it. So of course it would change. That's how I think of it. And so you cannot look at things, and how do you really compute with them? That was the naive question with which I started asking questions and researching, like from an outsider's perspective. We will get there. We have some methods that pre-exist even the idea of quantum computers or machines, quantum physics in general, that can help. But before that, I would like to tell you about Euler and Kolmogorov. So Kolmogorov, of course, the guy behind probability theory, formalizing it. Probability theory, we have known it for a long time, but to formally formalize, to rigorously write down how probability works. That was very recent. That was just a bit before quantum physics came into being. And Euler, the guy behind graph theory, how to cross the 7 bridges of Königsberg, for example. If there are multiple paths you can take, how do you go through them? How do you make sure that you have gone through every given possible path? Or how do you make possible think that how do you make sure that you have gone through every possible node? That could also be very important, and they might mean different things, whether you are thinking of going through every node in a graph or going through all the paths in a graph, whether you are following a Hamiltonian cycle or a Eulerian cycle. So Euler, Hamilton, these guys, I meant the times, and I am mentioning some scientists and mathematicians or logicians by name because, well, maybe their individual name does not matter so much as what they did and how they influenced the times after that. So because we have graph theory and because we have probability theory, we can build quantum AI or a post-quantum AI or even a traditional AI using these same old principles where we just say, yeah, we have a graph and it's a, let's say, Bayesian graph, or it has some notion of probability in it. So every time you do some branching, it follows Kolmogorov's formalism of probability, but at the same time, you are following Euler's formalizations of a graph. It said something about abstract universes and emergences, and that is one thing I would like to bookmark and come back to you later. Yeah, so we have these computations, and I told you that we can have strings or symbols as inputs in our computers, and that doesn't always sound interesting because sometimes we might want to enter a whole video and see some computation happening on it, or you might want to feed it some more complex object than just strings. Like enter your name, and it says hello and your name. That's 101. That's the very first thing you do when you do programming. You make something print hello world or something. That's a string manipulation. But what else could you do? So what kind of objects could you have in a computer in the modern sense, when you're actually doing software, not just theorizing about it? Then you would have this notion of set comes in different flavors. You could just think of a bag of dots, like a heap of things put together. Or you could have like a tuple kind of arrangement where you know that this is a finite sized 7 element or 5 elements in this set kind of thing. somehow it allows repetitions. You could have a graph. A graph is just a set of vertices, and edges like a set of sets. If you have a set of sets, then you have a hypergraph. If you have where essentially the only difference is that any path, it can connect more than two edge points, nodes. Any edge can connect more than just two nodes, and then you have a hypergraph, and it's formally it's just a set of sets. And then you can also think of things can be a finite collection of objects, but things can also be infinite, and within infinity you can find two major flavors, and we can do further classification of infinity. But infinite data or streams that come to us infinite in an infinite sense, they are always coming to us. They will never stop coming. Those things we can think of either as a convergent series or a divergent series, or as a very random series where we don't know what to expect next. But sometimes when it is either a convergent or a divergent kind of series, you can essentially skip ahead to the convergence if you want. Like, there's this joke where the barkeeper is asked to give one glass of beer, and then he does. Then he is asked for half a glass of beer, and then he does. And then he is asked half of what he gave last time, and then half of what he gave last time. And the barkeeper is supposed to keep on giving the half of what he gave the previous time. And if that is happening, if the barkeeper is smart, he can just give the guy, instead of giving him a smaller amount of beer for all of eternity, he can just give him 2 glasses of beer, be done with the night, and move on to other customers. When we do programming, we often have to think in these terms. Can you just skip past and just fast forward to the answer, even if there are infinite number of steps needed? Let's get there. Because at some point, there was Zeno, like in the antiquity time, he was worried about how do we ever cross across infinite number of steps, because going from any one place to another means going half the distance. And then that also means going half the distance, which also again means going half the distance. And this barkeeper, who is smarter than Zeno, perhaps, he just says, okay, take 2 glasses of beer, you're done. So, it's one of the ways in which we can think about infinity within computer science when we are dealing with equations, with flowing things, converging or diverging specifically. Another way of thinking about things, types of things, is product or a sum. And here what is happening is when you're taking a product of something, in the Cartesian product sense, you just look inside a set A and a set B, and then you just make all the pairs with elements from sets A and set B, and you have a nice grid, which you can say A cross B. That is a Cartesian product. A Cartesian sum would be something like you can have either this thing from A or you can have this thing from B. And if you have that, when you have either something from here or something from there, you have a sum of things from A and B. And if you have them both together, you have a product from A and B. So you can see that the Cartesian product actually is the thing that generates X and Y axis in the Cartesian grid. They are named the same, not out of coincidence, because it really is essentially the same kind of thing. So in physics, we think of the space-time axis, like the 3 axes of the space and 1 axis of time, as a given. In mathematics, in computer science, nothing is given. You have to construct that abstract universe within which you are doing the computation. And so, yes, we do have Cartesian grids every once in a while. Like even the software in which I'm doing the presentation, it depends on things being Cartesian, because once things are Cartesian, I can apply all of the things I know from linear algebra. So even these objects, like in this particular thing, example, you're seeing this, these things are objects, these deck of cards, these are the objects that we are working with. These could also be different other components. So the idea of an object could be also a web component, could also be an object. And it does not always have to do something to do with the object-oriented programming thing, where they have some bad ideas about what it means to have an object, which is sometimes frowned upon by the rest of the theoretical community. But it does help a lot in enterprise software development. So this object-oriented programming, it's a taboo topic, but objects themselves are not taboo. They are everywhere within mathematics, mathematical objects, how to build them. That has been the whole reason why we have computers in the first place. We were not originally interested in computers. We were interested in cracking codes. We were interested in doing numerical computations. We were interested in answering the more fundamental and bigger questions of mathematics. That's how we have these objects. Anyways, so all these web components that you're seeing here, they are in some sense objects as well. So an object could be something that in this example, an object in the monoidal object sense, an object is anything, a set often, which is embellished with a nice new operation called, let's say, it's you can call it anything. This operation could be, let's say, like a multiplication operation, which is associative and binary. So which means there are two operands, and there is one operator and two operands. And then from there, you get to something else. If what you get by mixing these two operands is also a monoidal object, it's also a part of that set. It means that there is a closure from that set. If you do this associative binary operation, you still end up within that set itself. So that is a closed monoidal set. Another thing monoidal object has is if you ask it who it is, it will tell you who it is. That's the identity operation. Any object always has this function which gives you the object itself. Why have that? It sounds so trivial, but in terms of composing something, in terms of putting things together, sometimes we should be able to, one of the components might need to ask the other guy who they are and then get the answer. So that's why we need the identity morphism. But these monoidal objects, they basically are very, very useful. It's like how plastic is useful for us, but yeah, I don't think that's the best example, but essentially like a thing that can be used almost everywhere, like how the chemical components that make up a plastic or plastic-like things, we see them appearing almost everywhere in everything we see. Monoids are a bit like that. They are the building blocks, like the bricks with which we build the rest of reality within mathematics, within computational mathematics. So for example, free monoids, these are things that I was telling you earlier about, traces back to the very origin of our category, like of our universe, in a sense, in the sense that, I was trying to get to the full screen version, sorry. So a free monoid, if you have strings, streams, lots of your systems might produce logs where you're monitoring certain things. Think of free monoids, because the string that is still there and something new you are adding to it, that is associative operation. And maybe we can think, oh, is it really associative or not? But it's actually just not commutative. It's not an abelian monoid. It can't be commutative in this sense, but it is still associative. All these string composers which build you bigger and bigger streams by adding something to it. Then you have these monoids which can tell you, give it something, and then if what you get out of this associated binary operation, and let's say if that thing is not within the set itself, then you say, oh, we are going outside the set. This is not allowed. So because of these transition monoids, you can find out which transitions you're not allowed to have, or let's say which syntax you're allowed to have. So you can check whether a given program or given a robotic blueprint for a robot or other structural things, they are correct or not. When you want to check whether a conceptual structure is correct, you check the grammatical correctness, and you still can find monoids helpful there. When you are taking the traces, like events leave a trace, in a quantum system more so. And again, the conceptual object running the soul here for us is a history monoid or a trace monoid. Then there are things that are monoidal categories, and I will get to what a category is in a bit. But if you have a symmetric monoidal category, and I found out about these things from a very recent talk. So apparently, symmetric and braided monoidal categories, they also can model the notion of concurrency, of how things go in parallel with each other. Maybe they intertwine at some point and then they still go on in parallel. So this whole idea, it can be modeled computationally using a symmetric or a braided monoidal category. So we like things which provide us a lot of things. And in category theory, the promise is that for most of the things you will find out within this system of thinking about mathematics and computer science specifically, but maybe someday also physics and other areas of human knowledge. And by the time I'm coming to category theory, I'm coming to the last 30, 40 years, specifically the last half of the century, where computer science has become much bigger than what it used to be. And theoretical computer science especially has actually gone farther away from, in some senses, from the practice, because as researchers, we do things that are 20, 30 years ahead of the industry. And we know that when I work on a certain Idris project, it is not a programming language used in production. It has quantitative types, dependent type theory, and these type theoretical constructs are needed mostly for a computer scientist. And I am both a computer scientist and an enterprise developer, some architect in terms of the ceremonial title, which doesn't matter much, even if I were just any other developer. Certain things within theoretical computer science just feel unnecessary for the rest of the software industry, which is fine as long as we are getting there. Maybe not every fancy exotic thing that comes out of our research needs to go into practice as a technological piece somewhere. But in a category theory itself is something that is not always known how it applies in this particular case. I have talked to mathematicians who are not aware that category theory is like a big part of computer science by now. But it is, and there are certain things within it that make it very, very appealing for us. One of the things is that, yeah, there is this associativity notion within a category as well, because we built up category initially thinking of monoids a lot, I think, from how it has been constructed. So you have objects and you have morphisms between objects. Morphisms could be a function, could be a linear map, could be a transformation. A morphism is, in the operatic sense, it's just an operation. It's something you can do with a given object, and so that you get somewhere, get a value out of it, or something happens. A morphism is very abstract, a generalized notion of what a function could be, or what a linear mapping could be, or other operations that you do within mathematics. Like even a relation could be a morphism in certain categories. And there's also the notion of order, which is defined more so like in a partial order set, a partially ordered set, like a poset. You know that there are going to be certain things in the set that come before certain other things, and that thing itself has another thing next to it, another thing before it. So this order also gives rise to ideas like, are these two things that are both at the second place in the order, are they equivalent? Because so in the terms of computation, it would mean that it's the same thing, so let's just repeat it. Or it could be like, they are different things, so let's do it twice separately. And finding these equivalences in computation is something that, for example, a Haskell or Agda or Idris language compiler would be able to do for free for you. because it might understand, oh, this thing is associative. So when I do this first and then do this first, it doesn't matter. Like that notion is even stronger in commutative or abelian objects. Yeah, but the category theory that I'm interested in mostly, especially for our purposes, in terms of computation, in terms of building a foundation for artificial intelligence, for example, uh, most of the time graphs show up at every level of the computation. The whole structure of the computation itself is graph theoretic, and the data structures themselves might also be graphs. While generating graphs, I have found out that these notions of anamorphism and katamorphism, again, they are some morphisms, right? So a graph could also have anamorphism, where some same repetitive actions, and again, these are monoidal graphs, which can repeat that associated binary operation. So on themselves, they have a new thing and themselves, and you can keep generating new parts of a graph. And within logic programming, we have certain things not coming directly from category theory, but you can say, these are the branches of this decision tree where I ended up in a dead end. There's nothing ahead of it. You either go into an infinite loop, or the thing I'm trying to do is not working if I go this way. So what you say is you extract that knowledge that you cannot go in a certain direction in a certain part or a branch of a graph. You feed that information back into your knowledge base. So every time you try something, you try to extend a graph if you want to go somewhere within the graph, and you find out that where you are headed is really not the right answer, then you feed that system back into the system. If you feed that information back into the system. So in that sense, a hypergraph is a universal structure, like a stack or a queue, or all these other naive, small, simple data structures, like a hash map that you might learn about as a programmer, as a theoretical computer scientist. These data structures, they all can be created using hypergraphs. So this is a more foundational structure from where you can, it is a hypergraph in most of the cases, and I have some proofs and we can go deeper into the formal rigorous proofs. But I have proofs about how with hypergraphs, you can have the hypergraph as the initial object from where you can or even define a terminal object at the same time in a category, in the sense that if you have a category of all the different CS 101 data structures, I can find you how to go from that data structure to a hypergraph, but I can also show you how to go from a hypergraph to that data structure. So hypergraphs really are universal structures. Most of the time, even just a graph is a universal, somewhat of a universal structure. And because we can do anamorphism and katamorphism, which is we can extend the graph by doing some repetitive actions, or we can also reduce the graph, cut the graph, like think of it as cutting your hedges to maintain your fence or some sculpture in your garden. So katamorphism is trimming different leaves and branches of the tree in the graph sense. So if we are able to do this both, we are able to maintain a graph that represents the model of computation itself. This happens a lot within AI, within software architecture, at a civilization, for civilization scale projects. So as an architect, if I'm involved in a civilization scale project, I think of nothing more than graphs. I cannot just do things using simpler primitives. But in one sense, graphs themselves are the simplest of all. So maybe that fits. And also, like I said earlier, we need to have a better relationship with infinite things and infinitesimal things. We need to be able to calculate what it means to, let's say, have 1/128th of a very small number. And the way we do computations with numbers in computers, the information encoding that we have is very lossy. So in reality, a lot of things, they might actually be a real number. But computers are not capable of displaying you a real number. Whenever a computer is showing you something as a real number, know that it's lying, because it is not theoretically possible for a computer to show you a real number unless it is doing that as a symbolic reference. You can give me symbolically what is the value of pi, but you can't give me the real value of pi from a computer because it is infinite. But even when there are finite values, which are, let's say, really high precision values, essentially lots of things after the decimal, or any very large value, these are things that are difficult for computers to deal with. But when you deal with these things in the category theoretic sense, infinity is very easy. We can have infinity for breakfast. It's something I tell my students often. In languages like Haskell, where everything is lazily done, you can say, yeah, I have an infinite list of things. And then somebody asks you, okay, give me that list. Then you say, hey, wait a minute, I won't give you the whole list. I'll give you one item from the list every time you ask. So every time they ask, you just find out what the next item in the list is and you give them, but you don't find the whole list before they have asked. And this is lazy evaluation. This is how we deal with infinity. One of the ways in which we deal with infinity, like in a lazy language like Haskell on the screen. There are other languages like Idris, which do not make everything lazy by default, but you can add lazy or infinite in terms of in front of certain types, and then it is annotated as something that is infinite or something that is evaluated lazily. So you can do an infinite amount of those anamorphisms or catamorphisms or any morphisms for that matter. So now we will be wrapping up, and I think this is an inverted talk in one sense, because I have inverted the idea that somebody introduces themselves when they start a talk. So in the final 4 slides, I'll be introducing myself, going back through the history of computer science once again with you. So yeah, CS is not just about computers. Computer science is not just about computers. Philip Wadler, who is very famous for introducing the notion of monads, which derives from the notion of monads. He once said that computer science is not about computers, and it's not, any decent science does not need to claim to be science so explicitly. It can just be a logy, or there are better ways to say that something is a science. We're using suffixes, but yeah, like and also this whole field, naming certain things differently just because you can create new things out of it, does not make sense, because most of computer science is mathematics. One of the things undergrads, you can see them being surprised that they go into computer sciences thinking they will be creating games somehow, and it will be similar to playing on a video game console. Or software guys who think, oh, why will we be able to do so and so financial trading with this software? And they think that our primitives are those web components, or are those fancy looking video games. But the primitives we work with are entirely mathematical. See, again, computer science initially and even till now was a means that emerged from mathematics. It is not in itself a separate thing, strictly speaking, but we can find some use of claiming, okay, this and this area is computer science, and this area is quantum computing, and this area is physics or mathematics. It's just necessary for being able to talk more efficiently. But maybe saying computer science is about computers is like saying physics is about building bridges. Computer science is a lot more than just that. And it was initially about answering uncomfortable questions within mathematics. Like I said, can we have a foundation of mathematics? Is the foundation axiomatic? Can you have a set of axioms, which, like in Euclidean geometry, we have 4 or 5 axioms. And then with that, you can construct all of Euclidean geometry. So does that apply for rest of mathematics? Can we have everything as a set, like a set equipped with associative binary operation and identity is a monoid. So can we just keep equipping sets with different things and end up with foundation of mathematics? And by now we have said maybe sets have problems. By the time we came to Russell's paradox and other important realizations, we said, okay, let's work with typed sets. And then the idea of types was born. And around the same time in the 1980s, the idea of category theory emerged out of all of these new necessities. We have had different models of computation. The Turing machine itself is a sequential model in a way, because it looks at the infinite tape that you feed into a Turing machine. It has a set of symbols. So there is a sequence that it is reading. And because it is reading a certain sequence of symbols, you can think of it as a sequential model in that sense. The input comes as a sequence. In the functional sense, everything is a function. In the church lambda calculus formalism of computer science, even numbers are functions. Every number can be represented as a function. If you so you could start, let's say, 0 is the zeroth function. It always returns you 0. And what is the next one? Well, you just apply a function to the function, and then you get 1. And what is the next one? You apply the function again to the function that you applied to the function earlier, so now you get 2. So you always get from 0, you get the successor of 0, then you get the successor of 0 again, and the successor of 0 again. So in computers, in functional sense, everything can be thought of as a function. And for category theory, that is important. And I will, and also for quantum computers. When we think of a thought experiment of how to build a RAM or a hard drive for a quantum computer, in the theoretical sense, we will see how that becomes relevant. Another thing we look into a lot is how to combine things. We have combinational patterns. Combinatory logic is a big field. Things can simply be combined without thinking of all these formalisms as well. And then there is the idea, and the biggest thing that I would like you to take from this talk is Curry-Howard-Lambert isomorphism. So Curry-Howard isomorphism on its own means things that you can do in logic, things that you are the same things that you can do in programs. Why? Because it's basically a mirror. Everything that we used to do in programs by construction, we derive it from logic, and everything from program derives from logic, and vice versa. I don't know which one I said first. Anyways, so things in logic and things in programming, there's some sort of isomorphism. When you're using typed programs where every variable has types, things can be very logical. Also, untyped programs can be logical. But in the Lambert part of the Trinity, the big holy Trinity of mathematics and logic and category theory, the Lambert part says that you can have an isomorphism from proof and logics to a program. So the program can basically be a proof of the logical proposition. Propositions are types, and programs are the proofs. If a type is inhabited, you have a proof for a logical question. If that type is uninhabitable, then your proposition can never yield an actual instance, so it's probably false. We don't know how to deal with that. So, but you can take all of these things into the category theory world and just live there. Because in the category theory world, you can do logic, you can do programming, you can generate programs, you can generate different logical calculus. And what are the things you can do in category theoretic world? These days, almost all the quantum processes that I am familiar with, just an undergrad level of a semester or two from quantum physics, I'm familiar with some simple quantum processes, and I have seen those few things being ported over to category theory, modeled in category theoretic terms. And now, since we can do them in category theory, it also means we can do them in programming. We don't need to wait for a quantum computer to do quantum programming because of Curry-Howard-Lambert isomorphism. So essentially, if all of us start doing quantum programming right now, we have the type checker, we have all the grammar, and we have all the framework to create, edit, rationalize, reason about those quantum programs, even using classical systems, because in a large part because of Curry-Howard-Lambert isomorphism. We cannot run these programs. We can maybe put them in a quantum simulator, but there's nothing really stopping us from writing quantum programs. So once we are able to write all these programs, we would also want to be able to access them. And this whole idea in a Turing machine was that every object, like a Turing object, has a action table. Also later in object-oriented programming, we did the same. Every object represented came with its own action table, which is essentially the kind of things it can do. So think of having lots of these computational objects. Each of them have their action table of things that they can do. And then you can randomly access things from somewhere. That would be the dream. That is the random access programming programs model, the random access stored machine. So that is the history. And how does it really play out for us these days when somebody says they are a software guy? People who study computer science and people who study software engineering, they both end up getting called a software guy or a girl. Guy is very gender neutral as well. And we are not. Not everybody who studies computer science is a software engineer. Like, very few people are interested always in having a career. Not very few, very few people are not always interested in that. So most of them go into software, but that's not the only thing we do. In fact, many professors in computer science, some of the biggest minds I have known, they don't know how to do programming. They have maybe not done programming in 30, 40 years. They still are computer scientists. Because like you see, most of what we do, we are thinking of monadic objects, monoidal things, and we are thinking of category theory. We are thinking of logical calculus. We are thinking of creating a new metalogical work, let's say, for the quantum physicists who now need a slightly different version of logic because they are seeing certain different things. So we do this metalogical framework level stuff, category theoretic stuff, but everywhere when we have certain stuff, certain objects, these are abstract objects. And initially, I used to think I'm a software guy. Now I studied computer science, and I was very convinced that there is more to it, but I had given up on the idea, and I just said, for a living, I'll just be a software guy because it seems easy. And I did not have to really spend too much time understanding different frameworks, because as a computer scientist, it was easy for us to understand the same frameworks for making software. But at some point, you just say, I think, if I am something beyond just a software guy, is a bachelor's of science, BS degree, is it enough to be a scientist? And in the same sense that computer science, it is having to claim to be a science by the title itself, people are very confused. When is it that they become a computer scientist? What is the critical point after we can say, yeah, you are a scientist, computer scientist now? Because most computer scientists are physicists, mathematicians, logicists. I have some instances of operation researchers within economics becoming computer scientists because they found great ways to do their operations research algorithms. Initially it was a means that emerged from maths to be able to answer foundational questions about mathematics, to be able to compute certain computable numbers, to even think of what can be computed in the first place. So now it's about the formalization. It was formalization of mathematics, right? And now it is the formalization of something even more deeper than mathematics itself. Like mathematics comes from rational choices, logical choices that we make about abstract concepts, abstract mathematical concepts. So now my computer science, my CS, and I don't say computer science often, I usually prefer the term computational sciences, because then it's more clear that it's not just about computers. So my CS, my computational sciences, are about the formalization of rationality itself. Before it was about answering uncomfortable questions, now it's about solving practical and urgent problems. We were asking, can we have a foundation of mathematics? Now we say, no, we can have a platform which creates platforms for other foundations, for economics, or a new model of economics, a new model of banking, for example. These things can be formally, rigorously written down, encoded. And some of these machines could be quantum machines, some of these could be classical, and the overall computer that is built in itself does not have to be either quantum or classical, or it can be something new entirely, but the theory essence of computation will remain the same, right? So before we were thinking axiomatic, is it theoretic or logical? And now we are thinking, can I do that using, say, projective geometry? Can I do this using dependent types? Can I do this using category theoretic formulations? Are this and this the same, or is there like a natural transformation up to the isomorphism? These are the kind of things we think of. Is there that is a more fancier way of saying, can you do diagram chasing and end up to the same places through two different ways? So now we think of these same things in a slightly different term. Can we have a complete set of axioms? No, maybe not. It would imply that there are a finite set of things to know about, and you know all of them. Maybe that's not how knowledge works. So now we think of, can we have a linked data with which you can semantically link different concepts? And instead of completeness, you can think of complete linkages, that essentially linkages that connect you to everything. So yeah, and then we have some standardization in the case of semantic web, or semantic standards are there for the web, and so we use that for consistency, but also for other reasons. Standardization itself. Consistency and completeness are these two duals. If you have one, you can't have the other. In a certain first order logic framework sense, in certain higher order logic, this might not be a problem. And decidability is essentially more generalized into computability. If there is anything that can be computed at all, it can be computed using a Turing machine. So if you feed it into the Turing machine, if it can compute it for you, voila, you have an answer there. So we talked about monoids, a more evolved version, if you have a monoid in a particular kind of category of endofunctors, then you have a monad. We will not get into that, but one thing I would like to tell you about monads is, just like earlier I was telling you how a Cartesian product is generating, let's say, a two-dimensional or a three-dimensional space, which can map into the physical space itself. If you play long enough with comonads, out comes spaces, Cartesian, Hilbert, these spaces, but also outcome hypergraphical spaces. And let's say you are trying to model some parts of causality, some parts of physics, some parts of some quantum processes. Those things, I mean, most of the time you would find out that you are using monads for if there is a computation that has an effect into an outside world, then you use monads. If the computation happens within a particular computational context, like a wrapper which hides something within it, then also you need a monad. So these abstract notions are useful in a lot of places, and we are often surprised how often in every scale they are used. So yes, there are other interesting things like sequences become streams, functional programming. These days we call it functional reactive programming. If you are always working with streams and infinite data structures and you're always reacting to changes, then you say it's not just functional, it's maybe a bit more, but it's still pure functional programming. It's just a new way of talking about it. And for concurrent models of computation, one of my contribution to this field, if ever there will be one, it's about a unified access architecture for all kinds of data, whether it's in a quantum system or even within classical system, whether it's in a distributed Hadoop store or whether it's in some other SQL, NoSQL database. What I have is a universal access architecture. So like there used to be Curry, Howard, and Lambert, and now we have other versions of the same things. Like there is mathematics, there is quantum physics, and then there is computer science. Put them together, that's also a new trinity that we can be chasing. This isomorphism is more of an interpretation, but there are certain proofs about how it applies. And you can find similar multi-domain redundancies, like people find out things within logic, and then 30 years later they find out again the same things in programming, and then maybe somebody finds out again in category theory. We can basically fast forward through that, do all of this together, and get to the future faster. And so most of these things, I had summarized it and I had put it in some small notes. You can see my bad handwriting here. This is an invitation card for an art exhibition. I met a wonderful person, and I'm happy to say that I'm in love with her now and together. But initially when I met her, I was also having the same crisis as a person. Is like, am I a computer scientist? What do I work on? Can I put down all these things on paper? Can I tell you the history of computer science of my field in a simple place? And this is essentially the paper. This is the napkin tissue on which I wrote down all the things I was thinking of. And I had thought of loops, and we were talking about loops. So this invitation card is called Loop. So in a sense, this summarizes almost everything, my history. And you can see that the history of computer science and the history of my career, they have some parallels, but also that my love life is built around sets of similar conversations. And if I can introduce myself formally and much better to an artist who is completely far away, more far away than a quantum physicist who studies quantum computers and quantum computer sciences, then really almost all the fields can actually understand each other. We just need to be able to, like, I want to come back to the initial point, create a language, create the grammar of that language to be able to talk to each other. And right now, that's what we need to do for, let's say, physics. We need to be able to talk to physicists, and physicists need to be able to talk to us. And so we can essentially agree on why and how things could be, and what the goals are. For example, I could stipulate that not having a universal Turing machine, a quantum version of a universal Turing machine, would make us not reach that goal. It means we have just quantum calculators and not quantum computers. And finally, if we still have some time, I have one more slide. This is just an example. And I do not know enough about Lagrangian mechanics to actually talk to you about it. But while researching on this talk, I found out that there are examples where I can claim that logic builds up the rest of physics. And intuitively, it might make sense, especially to me as a logic semantics person. There is a steady action principle. It used to be called the principle of least action, but it's not really least. There is still some sort of optimization, but it not goes towards minimization. But I am calling it the minimum action thing here. A light photon, a light particle, or other things that reflect off of something or that interact with other surfaces. Usually they have a path. In the case of light, we can see that light, the photon itself, is minimizing the distance in time, not just the distance in space, but the distance in time. And from there, you can derive how optics would work with reflection, refraction, and different cases within optics. You can explain, you can create glasses like the one I'm wearing. In fact, if you take this idea further, you can outcomes all of Newtonian mechanics, outcomes the theory of relativity. These things emerge out of more fundamental principles like the steady action principle or the Noetherian symmetry related principles that I told you about earlier. And what is happening here and why this is relevant for us is that we are seeing that logical calculus or some set of logical propositions, they are building up the rest of physics in this particular domain. And that's essentially something to learn from. Like the photon itself is not a computer, but it always finds the simplest path. How does it do that? It does not need a supercomputer or a quantum computer to tell it where to go. It is in itself doing what it needs to do. And so we need a certain new set of principles, certain new foundational principles, similar to what happened with Lagrangian mechanics, but for quantum computing, where we can have, for one thing, we would have to have these monads, which allow us to do computation without having to look inside. Because from what I gather, observing a quantum information is a bad habit, let's say. Another thing would be we need to create some foundation, logical foundations, where non-locality is allowed. Anything within logic, within quantum, within computer science, does not prevent us from having non-locality or from having multiplicity or superposition of a state. All the state machines and Turing machines that I have talked to you about, they can also be quantum machines in theory. And there's nothing really like in classical physics, there is a classical notion of reality, and that does not map onto classical logic. Classical logic still does allow for quantum phenomenon to be modeled within it. And to really be convinced of how this works, I had to be convinced of how Curry Howard Langbeck isomorphism works, and and how it actually means essentially that if you can have a categorical model, like a dagger compact category comes to mind, where you can represent finite dimensional Hilbert spaces and model things that would happen within it. So when you're doing these things, essentially in category theory domain, you have a way to port it over to the rest of the universe, rather to quantum physics and to quantum computers, and also to classical computers. If they are not going to run those programs, if they are just going to type check it, validate it, then even classical computers can use those programs as inputs. Anyways, these are moonshot ideas. Just because I can create you a constant morphism or a constant function that always gives you the same value, in theory, does not mean that you can also achieve the same thing in quantum using quantum physics. But when we are able to do that, we have one thing I had promised earlier was we will be talking about using these monoids that we could talk a bit more about, especially how could we have a quantum hard drive or a quantum memory, because it goes back to the idea of universal Turing machine. A Turing machine should be able to have different objects which have different action tables and be able to just make some of these action table items happen. enact those action tables. So how do for that you would need to have a storage a system where you can read all these programs. And reading programs is fine as long as you have written it using classical bits. It's easy, you can read it. But the programs themselves will be dealing with quantum data. And then you and these data, they are like one-time use data only. The moment you have seen it, you have changed it. So maybe you can access the data only once, and then you don't know what happens to it afterwards. So in these kind of processes, one of the things you could have is have this notion that, for one thing, you don't have to look inside the data. You just look at the descriptors of that data from where you derive what kind of data is inside there. And since you know the kind of data inside a particular container, you can work on that knowledge that you have about the type of the thing that is inside, not the value of the exact value of the thing inside. As long as you know that the thing that this quantum algorithm calculated for me is, let's say, the probability of this particular branch being correct or not, then you don't have to really look inside it, but you have to still be able to deal with the idea that this number represents some probability. So you might know that, yeah, this represents something between 0 and 1. So with that information already, you can do a lot within computation. So you don't always have to worry about what is the value, but there are times when you have to read the value. And after teaching a bit about category theory and Dagger compact categories, I would usually leave it to the reader or the viewer as an exercise. But one of the ideas that many groups of students have often come up with, including myself, is that you could have a category in which the initial object or the final object, or both, in that case it's called a zero object. You have a category where there are initial and final objects that are a category of these things are constant functions. Constant functions in mathematics always give you the same result. So if you have a category where the zero objects, which means the initial and the final objects in these categories, are constant functions, but there is a guarantee that from any object in that category, you can reach to this either initial, you can always reach to this final object from any object you started with. If you can give me a morphism that gives me the constant function representing that value, then what you have given me is, instead of saying, yeah, I have stored this data for you here, you are saying, if you ever want this data again, just call this guy, this function, and he will give you. So this is a store in the quantum store, in the quantum hard drive. You would not have to have a SD table, like it says on the slide, like where all these things are stored. This notion of being able to store things, we might need to change that, because the future of quantum computing is not about repeating everything from classical computing. Maybe in the quantum world, we don't need hard drives and RAM anymore, because they solve a particular problem within classical computers. Nobody needs a hard drive. Nobody needs a RAM in their machine. If the machine itself can always remember something without needing a hard drive, maybe the processor itself can somehow hold on to all the data, then we wouldn't need a separate unit called a hard drive. Because the information is needed only on the level of the processor. Like everything else is the auxiliary part of the computer, the RAM and the hard drive, or even the database. So as long as the processors can always find you the constant functions, or they have a guarantee of a morphism that always takes you to a value, then category theory has given you a RAM or a hard drive in a simulated version for free. Like, you don't even need it anymore. So those are the kind of things we keep concluding in the theoretical sense, but it is, of course, very far away from reality. Like we still would have to find a way to have a quantum to have a constant morphism in actual quantum physical sense. If we are able to do that, we have a quantum RAM or a quantum hard drive. So Once again, a universal Turing machine is the goal of quantum quantum computers. Maybe bigger goals than that, but at the very least, we need to be able to create a universal Turing machine. And one more thing other than that, category theory does seem like a way to get there faster because of Curry-Howard-Lambert isomorphism. Whether you are talking to a computer using logic, whether using programming, whether you are talking to another human being, another physicist using logic. So in one sense, you're using logic. In the other sense, you're using programming if you're talking to computers. So the idea of category theory is whether you're talking to humans with logic or whether you're talking to computers with programming, you're still talking, and you can do all your talking in category theory itself, where things are a lot faster, where things are more intuitive and diagrammatic. So with that, I would like to yield the floor to the questions from the audience. And I think I must have gone a bit over time.
Okay, Rishabh, thank you very much. So let us give Rishabh a round of applause. I mean, this applause won't be virtual because sound is physical, right? So I will join me on that, guys. Yeah, awesome. Thanks, Rishabh. Yeah, I mean, very interesting, right? A lot of these ideas, for example, set theory and monoids. I'm not an expert, but I have heard about it here and there, and I came across this thesis that talks a lot about set theory and how it relates to quantum mechanics and ultimately to quantum computing, right? So a lot of things to digest for me. I mean, obviously, I'm not an expert. I will have to look up a lot of these terms, but do share the slide.
Yeah, I will.
Us,
I will also share the explained, extended version of it along with the software with which I'm using to present you. Because the software itself is a bit more interactive. For example, if you go to the initial slide here, then you can see that this is the current slide. So this is the identity morphism. And here you can, when you are looking at it in the future, you can see a bit more. Like you can see that there is a spatiotemporal, domain and context, and historicity. And these are the 3 points within this slide. So these slides will explain themselves. So this whole software is so that you might be able to use it later. So not only the slides, but the present software which present the slides are also going to be released on my GitHub.
Okay, sure. So I think I'm also running out of time. I have another meeting, so I will take one question. Maybe if you can do that in like 1 minute, that would be great. So Abhiskar asks, do you see future? I see many youths running to the field of computer software, apps, AI, machine learning. Do you see future in that field of computer science? Or you can see future career path in computer science, computational science. So he's basically asking, a future in computer science, right? Software.
Yeah, so the career question essentially, how it would be if they pursue it. Another formulation of this question often to me is, should I study computer science or software engineering in the university? Because the question is often like, should I study physics or should I study, say, civil engineering or electronics engineering? Because in the same sense, like you could study physics and still know about building bridges, and you could study civil engineering and you would still know about building bridges. But are you really interested in building bridges? Then you should study civil engineering if you want to know more than just about bridges or about, let's say, structures, physical structures. You maybe want to go on the level of quantum physics or electronics. Within physics, if you want to specialize, you would go with physics and not, let's say, civil engineering in your undergrad level. In computer science, what happens is if you just want to make software, you don't have to study computer science anymore. You can just learn software. I have courses in Umbrella Academy, which is a thing I run as a volunteer, where there are free courses for anyone, even a high school grad, to become a programmer. It has really not much to do with theoretical computer science. So if you want to find a career, where finding jobs is a key concern. Then there are a lot more jobs in the field of software engineering and not in the field of computer science. But most people who do software engineering study computer science because it's just a great place to start learning if you want to learn about software. And beyond the difference between computer science studies and software engineering studies, there's also the matter of this whole field, this whole idea, this whole branch of knowledge. Should we go into that? And insofar as your question pertains to that, I would say, while going into that, please be aware that you are going into mathematics, you're going into physics, you're going into logic. And if those are the kind of things that you operate well with, then you could go into it. I initially, personally, I had got an acceptance